Good day. For today, we will be discussing isotonic solutions. When a solvent passes through a semi-permeable membrane from a dilute solution into a more concentrated one, the concentrations become equalized and the phenomenon is known as osmosis. The pressure responsible for this movement of solvent molecules across a semi-permeable membrane is called osmotic pressure. This varies with the nature of the solute, that is, either as electrolyte or as non-electrolyte. A solution having the same osmotic pressure as a specific body fluid is termed isotonic, meaning of equal tone, with that specific body fluid. The tonicity of pharmaceutical solutions to be introduced to the systemic circulation or mixed with biological fluids of the eye, nose, and bowel are considered by the pharmacist in their preparation and clinical application. This lesson introduces methods of preparing isotonic solutions using the sodium chloride equivalents, or E values, and freezing point depression. A brief overview of colligative properties shall also be covered to introduce tonicity adjustment methods. At the end of this lesson, the student will be able to first differentiate between the terms isosmotic, isotonic, hypertonic, and hypotonic. Second, apply physico-chemical principles in the calculation of isotonic solutions. And third, perform the calculations required to prepare isotonic compounded prescriptions. Physical properties can be divided into two categories: extensive properties, such as mass and volume, that depend on the size of the sample, and intensive properties, such as density and concentration, which are characteristic properties of the substance. That is, these do not depend on the size of the sample being studied. Apart from these physical properties, a third category known as colligative properties can only be applied to solutions. Colligative properties depend on the ratio of the number of solute particles to the number of solvent molecules in a solution, and not on the nature or identity of the chemical species present. That is, for as long as a solution contains the same number of solute particles in the quantity of the same solvent, they will have the same colligative properties, even though the solutes are chemically different. Examples of these include a sodium chloride solution and a potassium chloride solution, for as long as both solutions contain the same number of solute particles in the same quantity of, let's say, water as the solvent. Some examples of colligative properties are the following: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Now take note that vapor pressure, boiling point, and freezing point are all intrinsic or intensive properties, meaning these properties are physical constants of a particular solute or a particular substance. However, their lowering or elevation are considered to be colligative properties. Boiling point is defined as the temperature that is required to convert a liquid substance to vapor, while freezing point is the temperature at which a liquid turns into a solid. Another definition of boiling point is that it is the temperature at which the kinetic energy of the particles are sufficient in order to break the intermolecular forces that hold the molecules together in the liquid phase for them to transfer to the vapor phase. In that definition, we can see very clearly that vapor pressure and boiling point are related to each other. Vapor pressure, in fact, is inversely proportional to the boiling point of a particular substance. The higher the vapor pressure of a particular liquid, the lower is its boiling point. A substance with a high vapor pressure is considered to be a volatile substance, while a substance with a low vapor pressure is considered to be a non-volatile substance. Another definition of boiling point that relates vapor pressure with the boiling point is that boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. In that way, we can see why the vapor pressure is inversely proportional to the boiling point. If a particular substance has a high vapor pressure, it would need less energy for it to equal the atmospheric pressure. Whereas for a substance with a low vapor pressure, the more energy is needed to equal the atmospheric pressure. A more detailed discussion on these colligative properties will be covered in your other subject, which is physical pharmacy. For now, we will briefly discuss osmosis and osmotic pressure. Osmosis is the movement of water or solvent molecules across a semi-permeable membrane from a dilute solution into a more concentrated one. In other words, osmosis is the transfer of solvent molecules from one compartment that contains a lower amount of the solute particles to another compartment that contains greater amount of the solute particles. Take note that this movement of solvent molecules requires that there is a semi-permeable membrane that separates the two compartments. Although it may appear that this type of movement is against the concentration gradient, it is in fact similar to diffusion. Diffusion is defined as the movement of solute particles from a region of higher concentration of solute to a region of lower concentration of solute. Take note that compared with osmosis, diffusion does not require a semi-permeable membrane that separates the two regions where the solute particles move. Also take note that in diffusion, it is the solute particles that move and not the solvent molecules. Now let's go back to osmosis. Remember that in osmosis, the water molecules move from a dilute solution into a more concentrated solution. A more dilute solution contains less of the solute particles. So it means that this particular solution contains more of the water molecules. Now, if we will put our attention to the solvent molecules or the water molecules, we can see that osmosis, much like diffusion, follows the concentration gradient. But instead of following the concentration gradient of the solute, it follows the concentration gradient of the water or solvent molecules. The minimum pressure which needs to be applied to a solution to prevent the inward flow if it's pure solvent across a semi-permeable membrane is called the osmotic pressure. As previously mentioned, the osmotic pressure is one of the colligative properties of solutions. It does not depend on the chemical identity of the solute, but rather it depends on the number of solute particles in relation with the solvent molecules. One consideration, however, in determining the colligative properties is recognizing whether the solute is an electrolyte or a non-electrolyte. Electrolytes are substances that dissociate into ions in solution. Examples of electrolytes are ionic substances such as sodium chloride, potassium chloride, dibasic sodium phosphate, silver nitrate, and hydrochloric acid, as well as salts of organic compounds such as atropine sulfate, chlorphenamine maleate, phenylpropanolamine hydrochloride, sodium citrate, and others. On the other hand, non-electrolytes are substances that do not dissociate in solution, or when they do, their degree of dissociation is negligible. Many organic compounds, which are in their molecular form in solution, can be considered as non-electrolytes. Examples of this include glucose, sucrose, glycerol, urea, and even boric acid, an inorganic compound. If the solute is a non-electrolyte, its solution contains only molecules, and the osmotic pressure varies with the concentration of the solute. However, if the solute is an electrolyte, its solution contains ions, and the osmotic pressure varies with both the concentration of the solute and its degree of dissociation. You will see in the following slides how the degree of dissociation of electrolytes affect our determination of colligative properties of these solutions. Biologists and biochemists often take advantage of osmotic pressure when they isolate the components of a cell. When a cell is added to an aqueous solution that contains a much higher concentration of ions than the liquid within the cell, water leaves the cell by flowing through the cell membrane until the cell shrinks so much that the membrane breaks. Alternatively, when a cell is placed in a solution that has a much smaller ionic strength, water pours into the cell and the cell expands until the cell membrane bursts. These phenomena occur because of the differences in the tonicity of the solutions inside and outside of the cell. Two solutions that have the same osmotic pressure are termed isosmotic. Many solutions intended to be mixed with body fluids are designed to have the same osmotic pressure as a specific body fluid and are termed isotonic with that specific body fluid. Solutions of lower osmotic pressure than that of a body fluid are termed hypotonic, whereas those having a higher osmotic pressure are termed hypertonic. Pharmaceutical dosage forms intended to be added directly to the blood or mixed with biological fluids of the eye, nose, and bowel are of principal concern to the pharmacist in their preparation and clinical application. It is generally accepted that for ophthalmic and parenteral administration, isotonic solutions are better tolerated by the patient than those at the extremes of hypo and hypertonicity. With the administration of an isotonic solution, there is a homeostasis with the body's intracellular fluids. This, in most instances, preparations that are isotonic or nearly so are prepared. However, there are exceptions, as in instances in which hypertonic solutions are used to draw fluids out of edematous tissues and into the administered solution. Most ophthalmic preparations are formulated to be isotonic or approximately isotonic to duplicate ophthalmic tears for the comfort of the patient. These solutions are prepared and buffered at an appropriate pH, both to reduce the likelihood of irritation to the eyes, tissues, and maintain the stability of the preparations. Injections that are not isotonic should be administered slowly and in small quantities to minimize tissue irritation, pain, and cell fluid imbalance. The tonicity of small volume injections is generally inconsequential when added to large volume parenteral infusions because of the presence of tonic substances such as sodium chloride or dextrose in large volume infusion, which serve to adjust the tonicity of the smaller added volume. Intravenous infusions, which are hypotonic or hypertonic, can have profound effects because they generally are administered in large volumes. Large volumes of hypertonic infusions containing dextrose, for example, can result in hyperglycemia osmotic diuresis, and excessive loss of electrolytes. Excess infusions of hypotonic fluids can result in the osmotic hemolysis of red blood cells and surpass the upper limits of the body's capacities to safely absorb excessive fluids. Even isotonic fluids, when infused intravenously in excessive volumes or at excessive rates, can be deleterious due to an overload of fluids placed into the body's circulatory system. In this particular diagram, you can see very clearly what happens to different types of cells when cells are placed in isotonic, hypotonic, or hypertonic solutions. Take note that when cells are placed in an isotonic solution, there is a net zero transfer of water molecules from inside of the cell or from outside of the cell. The cells remain normal, or in plant cells, the plant cells become flaccid. When cells are placed in hypotonic solutions, there is a net inward flow of water, resulting in the breaking of the plasma membrane of the animal cell, hence the lysis of the cell. In this particular diagram, you will see the bursting of the red blood cell we call hemolysis. In plant cells, however, because of the presence of the cell wall, the inward flow of water will just result in the turgidity of the cell. The water that moves into the plant cell goes into the cytoplasm as well as into the large water vacuole of the plant cell. This will make the plant cell highly turgid, just like what you normally observe when you place fruits in distilled water. They become very crunchy. Now, when cells are placed in hypertonic solution, there is a net outward flow of water, resulting in crenation or shriveling of the plant cells, as well as animal cells. Because of the absence of the cell wall in animal cells, the shriveling would often result in the bursting of the cell, hence leaking of the cellular components outwards of the cell. In plant cells, the shriveling of the cell would simply result in plasmolysis, where the plasma membrane detaches itself from the cell wall. The calculations involved in preparing isotonic solutions may be made in terms of data relating to the colligative properties of solutions. Theoretically, any one of these properties may be used as a basis for determining tonicity. Practically and most conveniently, a comparison of freezing points is used for this purpose. It is generally accepted that negative 0.52 degrees Celsius is the freezing point of both blood serum and lacrimal fluid. When 1 gram molecular weight of any non-electrolyte is dissolved in 1000 grams of water, the freezing point of the solution is about 1.86 degrees Celsius below the freezing point of pure water, which is 0 degrees Celsius. That is a molar concentration of any non-electrolyte in water would have a freezing point of negative 1.86 degrees Celsius. By simple proportion, we can calculate the weight of any non-electrolyte that should be dissolved in each 1000 gram of water if the solution is to be made isotonic, to be able to see how we will be able to use this proportion that solve some problems. A solution of anhydrous dextrose with a molecular weight of 180 contains 25 grams in 500 milliliters of water. Calculate the freezing point of the solution. Remember that in the previous slide, we mentioned that a gram molecular weight of any non-electrolyte in 1000 grams of water would have a freezing point of negative 1.86 degrees Celsius or a freezing point depression of 1.86 degrees Celsius. In order to solve this problem, we will be using that knowledge and we will simply make use of proportion. Now, the first thing that we will have to do is we have to determine the amount of dextrose that is contained in 1000 grams of water. Now, in this particular problem, 25 grams of dextrose are contained in 500 milliliters of water. Take note that water has a density of 1 gram per ml. Therefore, the weight of water is 500 grams. Now, if 25 grams of dextrose are present in each 500 grams of water, then we can solve for the value of x, which is the amount of dextrose in 1000 grams of water. And that will be equal to 50 grams of dextrose. Now remember what we mentioned before, that a gram molecular weight of a non-electrolyte has a freezing point depression of 1.86 degrees Celsius when it is placed in 1000 grams of water. Now, the gram molecular weight of dextrose is equal to its molecular weight, which is 180 grams. Now, when 180 grams of dextrose are placed in 1000 grams of water, its freezing point depression is 1.86 degrees Celsius. Now, going back to what we have in the problem, we have 50 grams of dextrose in 1000 grams of water. And we can actually determine the freezing point depression of that particular solution. We can then cancel the 1000 grams or 1 kilogram, and we simply have to rearrange the values so that we will be able to compute the freezing point depression. So the freezing point depression, delta TF, is equal to 1.86 degrees Celsius times 50 grams divided by 180 grams. The delta TF, therefore, is equal to 0.5167 degrees Celsius, or approximately equal to 0.52 degrees Celsius. Now, the freezing point of water is 0 degrees Celsius. Taking that into account, we can then determine that the freezing point of the solution of dextrose that contains 25 grams in 500 milliliters of water is equal to negative 0.52 degrees Celsius. Now, that is one way for us to determine the freezing point of the solution. Now, there is another way by which we can compute for the freezing point of the solution, again, by determining the freezing point depression of the solution. And in this particular instance, we will be using the formula that is delta TF equals KF times M. M stands for the molality of the solution. while Kf stands for the cryoscopic constant of the solvent. Now, the molality of the solution can be determined as the number of moles of the solute for every kilogram of the solvent. To determine the number of moles of the solute, we simply divide the weight of the solute by its molecular weight, and then divide all these together by the number of kilograms of the solvent. Now, the cryoscopic constant of water is equal to 1.86 degrees Celsius per molal solution. The solution needs to be a solution in water, so this can also be stated as 1.86 degrees Celsius per molar concentration of an aqueous solution. Now let's go back to the problem. What do we know in the problem that we can plug in this formula? The molality of the solution can be calculated as weight of the solute, which is 25 grams, divided by its molecular weight, which is 180 grams per mole. And we divide this by the number of kilograms of the solvent. Take note that our solvent, which is water, has a weight of 500 grams, or it is equivalent to zero point 0.5 kilogram. Solving for the molality of the solution, we now determine that it is equal to 0.2778 molal. Plugging in the values, delta TF, or the freezing point depression of that 0.2778 molal solution, therefore, is equal to 1.86 degrees Celsius per molal times the molality, that is 0.2778 molal. We cancel the molality and we multiply the two quantities to get the same answer. 0.5167 degrees Celsius, or approximately equal to 0.52 degrees Celsius. Again, considering that the freezing point of water is 0 degrees Celsius. The freezing point of 0.2778 molal solution of dextrose is equal to negative 0.52 degrees Celsius. Now let's talk about what other information you can derive from this particular problem. You can see that approximately 5% of dextrose in water would have a freezing point depression of 0.52 degrees Celsius, or a freezing point of negative 0.52 degrees Celsius. Remember that the solution contains 25 grams of dextrose for every 500 grams of water, or 500 milliliters of water. Now, if we will assume that the 25-gram dextrose does not add to the volume of the solution, we can assume that the volume of the solution remains 500 milliliters. Now, we can determine its percentage strength by multiplying this by 100, and what we get is 5%. So a 5% dextrose in water solution would have a freezing point of negative 0.52 degrees Celsius, equivalent to that of the body fluids. We can also say that the 5% dextrose in water solution is an isotonic solution because its freezing point is the same as the freezing point of body fluids. Now let's try to have another example. The freezing point of a 5% solution of boric acid with a molecular weight of 61.83 grams per mole is negative 1.55 degrees Celsius. How many grams of boric acid should be used in preparing 1000 milliliters of an isotonic solution? Now, take note that boric acid is considered as a non-electrolyte because it has negligible dissociation, unlike many other inorganic substances. There are a lot of information in this particular problem. For example, we know that a 5% solution of boric acid would have a freezing point depression of 1.55 degrees Celsius. We also know that boric acid has a molecular weight of 61.83 grams per mole. We are asked to determine how many grams of boric acid should be used to make 1000 milliliters of an isotonic solution. So first, we will go back to the statement that we have already learned previously. Remember that a molal solution of any non-electrolyte in water has a freezing point depression of 1.86 degrees Celsius. And that is the reason why the cryoscopic constant of water is 1.86 degrees Celsius per molal solution. That is where that definition comes from. 1 molal solution of non-electrolyte in water has a freezing point depression equivalent to 1.86 degrees Celsius. In other words, a gram molecular weight of any non-electrolyte in 1000 grams of water or 1 kilogram of water has a freezing point depression of 1.86 degrees Celsius. We can once again use that information to determine the amount of boric acid in 1000 milliliters of an isotonic solution. So the gram molecular weight of boric acid is 61.83 grams. In 1000 grams or 1 kilogram, its freezing point depression is 1.86 degrees Celsius. Now, if we are to prepare a 1000 milliliters of isotonic solution, we will assume that the amount of boric acid that will be dissolved in the solvent does not contribute appreciably to the volume of the solution. So we can state that the amount of the solvent to be used in preparing the isotonic solution is also approximately equal to 1000 grams coming from the 1000 milliliters, which is the volume of the isotonic solution. And then we do not know the amount of boric acid X to be dissolved in such amount of the solvent. Now, what else do we know? We know that in order for a solution to be isotonic, its freezing point depression should be equal to that of the body fluids, which is 0.52 degrees Celsius. Now, we can then cancel out 1000 grams, just like what we did before, and then we simply rearrange the values in this particular proportion. Then we solve for the value of X. So that will be 61.83 grams times 0.52 degrees Celsius divided by 1.86 degrees Celsius. This will be equal to 17.29 grams of boric acid, or approximately equal to 17.3 grams of boric acid. Now take note that in this particular solution, we did not use the information that is stated in the first sentence, wherein the freezing point of 5% solution of boric acid is given as negative 1.55 degrees Celsius. In fact, we can use that information in this calculation for our second method. So let us just call this method number 1. There is another method. We'll call this method number 2. In method number 2, first, we recognize that in a 5% solution, there are 5 grams of boric acid in 100 milliliters of solution. Now, once again, we will assume that the quantity of boric acid does not contribute appreciably to the volume of the solution. Therefore, the volume that is 100 milliliters could also represent the volume of the solvent used to dissolve 5 grams of boric acid. Because water has a density of 1 gram per ml, then we can say that our solution is the same as 5 grams of boric acid in 100 grams of water. Then we will just solve for the amount of boric acid X that must be present in 1000 grams of water. And this is equal to 50 grams of boric acid. Now, if we have 50 grams of boric acid in 1000 grams of water, its freezing point depression is 1.55 degrees Celsius. Now, if we are to make 1000 milliliters of isotonic solution, or approximately if we will be using 1000 grams of water to prepare the isotonic solution, then its freezing point depression must be 0.52 degrees Celsius. Once again, we cancel the 1000 grams in this formula, and then we simply rearrange the values to solve for the value of y. So y is equal to 50 grams times 0.52 degrees Celsius divided by 1.55 degrees Celsius. And this gives us a value that is equivalent to 16.77 grams of boric acid. This is approximately equal to 17 grams, or 16.8 grams, approximately equal to 17 grams of boric acid, which we observe to be similar to what we got from the first method. There is in fact a third method by which we can calculate for the amount of the boric acid that is required to make an isotonic solution, and that is to use the formula that we have mentioned before. Method number 3. So in the third method, we will make use of the formula delta TF equals Kf times the molar concentration of the solution. Now, the delta TF that we need to get is the freezing point depression of an isotonic solution, which is 0.52 degrees Celsius. We know that the cryoscopic constant of water is 1.86 degrees Celsius per molar solution. Then we calculate for the molality of the solution, which is the weight of the substance, which we need to determine, divided by its molecular weight, which is 61.83 grams per mole, divided by the amount of the solvent needed to prepare the solution. Once again, we will assume that the amount of solvent to be used in preparing the solution is 1,000 grams or 1 kilogram. Now, what we need to determine is the weight of boric acid that is isotonic or that has a freezing point depression of 0.52 degrees Celsius when dissolved in 1,000 grams of water. So, rearranging our um, our formula, we will get this value. Weight of boric acid will be equal to 0.52 degrees Celsius times 1 kilogram times 61.83 grams per mole divided by 1.86 degrees Celsius per molal solution. So what will cancel out here? Take note that molality is essentially the number of moles per kilogram of the solvent. So what we will cancel here are the following. We will cancel kilograms, moles, and degrees Celsius. And we will be left with grams of boric acid. The weight of boric acid that is isotonic, therefore, is equal to 17.29 grams of boric acid. The same quantity that we determined before, approximately equal to 17.3 grams or 17 grams of boric acid. Now, it is up to you which method you will use for as long as the process that you perform is correct. It is up to you because it depends on which method you are most comfortable with in order to calculate for the either the freezing point depression or the freezing point of a particular solution or the amount of a solute that will make the solution isotonic. With electrolytes, the greater the dissociation, the smaller the quantity required to produce any given colligative property, such as osmotic pressure and, conveniently, as mentioned before, freezing point depression. That is, with the same molar concentration as the non-electrolyte, an electrolyte will have a greater freezing point depression than that of the non-electrolyte. Hence, the dissociation factor is multiplied by the value 1.86 degrees Celsius in this particular formula. The dissociation factor, also known as Van Hoff factor, commonly symbolized by the letter I, must be included in the proportion when we seek to determine the strength of an isotonic solution of an electrolyte. The dissociation factor is the ratio between the actual concentration of particles produced when the substance is dissolved and the concentration of a substance as calculated from its mass. For most non-electrolytes, the value of I is essentially 1. The value of I for many medicinal salts or electrolytes has not been experimentally determined. Some salts, such as zinc sulfate with only 40% dissociation, are exceptional, but most medicinal salts approximate the dissociation of sodium chloride in weak solutions. That is assumed to be 80% dissociated. Now, going back to the proportion that we used before, we simply multiply I by 1.86 degrees Celsius, and the rest remains the same. In that way, we can rearrange the formula in order to determine the gram or the weight of the solute per 1,000 gram of water to be equal to 0.52 degrees Celsius, which is the freezing point depression of an isotonic solution, times the molecular weight of the solute divided by 1.86, which is which is the cryoscopic constant or the freezing point depression factor of water, times I, which is the dissociation factor of the solute. If the number of ions is known, we may use the following values, lacking better information. Non-electrolytes and substances of slight dissociation have an I value or dissociation factor equivalent to 1. For substances that dissociate into two ions, the I value is 1.8. For substances that dissociate into three ions, the I value is equal to 2.6. For substances that dissociate into four ions, the I value is 3.4. And lastly, substances that dissociate into five ions, its I value, their I value is equal to 4.2. Now, in order for you to easily remember these values, just take note that we begin with two ions with an I value of 1.8, and you simply add 1 to the units place. 1, 2, 3, and 4. And then in the tens place, you simply subtract 2. So 8, 6, 4, and 2. So what we have are the following: 1.8, 2.6, 3.4, and 4.2. Now, where do we get all these values? Take note that if we lack information on the degree of dissociation of a particular salt, we assume 80% dissociation. That being said, let us try to derive these values assuming 80% dissociation. So let's begin with a two-ion electrolyte dissociating 80% in a given concentration. First, let us consider a two-ion electrolyte dissociating 80% in a given concentration. For example, sodium chloride. When sodium chloride dissociates in solution, it produces two ions, sodium ion and the chloride ion. However, if we assume that its dissociation is only 80%, then part of the sodium chloride solute remains undissociated. So after the dissolution process, this undissociated sodium chloride will not turn into sodium ions and chloride ions. We assume that initially we have 100 particles of the salt sodium chloride. Now, if there is 80% dissociation among these 100 particles, then we can say that 20 particles of sodium chloride remain undissociated and only 80 particles of sodium chloride dissociate into sodium ions and chloride ions. Because sodium chloride contains two ions, sodium ion and chloride ion, then we can say that there are 80 particles of sodium ions and also 80 particles of chloride ions. Take note that for every 1 mole of sodium ion, there is also 1 mole of chloride ion. So they should have the same number of particles. And because we only have 80 particles of sodium chloride that dissociate into sodium ions and chloride ions, then all of these will have the same quantity or the same numerical values, 80 particles. Now, in order for us to determine the I value for sodium chloride dissociating 80% in a given concentration, we simply add the number of particles after dissolution. So that will be 80 plus 80 plus 20 divided by the initial number of particles of sodium chloride, which is 100. And this is equal to 1.8. Now, look at the list on on the other slide, and you will see that substances that dissociate into two ions, like sodium chloride, will have an I value of 1.8 only when the dissociation is 80%. Now let us consider another salt, which is zinc chloride. So zinc chloride is a 3-ion electrolyte dissociating 80% in a certain concentration. Calculate its dissociation factor. So zinc chloride is a 3-ion salt that dissociates into zinc ions and 2 chloride ions. Now, in order for us to easily see how dissociation happens, I will simply write 2 chloride ions separately. Now, according to the problem, zinc chloride ion only dissociates 80% in a certain concentration. So there remains undissociated zinc chloride. Now, once again, let us assume that we have 100 particles of zinc chloride to begin with. At the end of the dissociation of zinc chloride, there would remain 20 particles of undissociated zinc chloride. Now, the rest are dissociated. So we have 80 particles of dissociated zinc chloride. Now, just like what we did before, we will now determine the number of particles of sodium and chloride ions that are present in the solution. Because 1 mole of zinc chloride produces 1 mole of zinc ion, then they should have the same number of particles. So we have 80 particles of zinc chloride, so we also have 80 particles of zinc ion. Now, because there are 2 moles of chloride or chlorine atoms in in 1 mole of zinc chloride, then the total number of particles of your chloride ion should be 160 particles. Or each of these will also have 80 particles. In order to determine the I value of zinc chloride, we simply add the number of particles, including the undissociated zinc chloride. So we have 80 plus 80 plus 80 plus 20 divided by 100. And this will result in 2.6, which is the same value that we saw in the previous slide. Now you can try if you will also get the same numerical values when you determine the I value for substances that dissociate into 4 or 5 ions. Now let us try another problem, this time a salt that does not dissociate 80% in a certain concentration. For example, zinc sulfate is a 2-ion electrolyte dissociating 40% in a certain concentration. Calculate its dissociation factor. Now, zinc sulfate is a 2-ion electrolyte producing zinc ions and sulfate ions. Now, because the degree of dissociation is only 40%, then 60% of this remains undissociated. Now, if we assume again that we begin with 100 particles of zinc sulfate, then there would be 60 particles of undissociated zinc sulfate. And the remaining are 40 particles of dissociated zinc sulfate, which become zinc ions and sulfate ions. Because 1 mole of zinc sulfate produces 1 mole of zinc ion, then the number of particles of zinc ion will also be 40 particles. And because 1 mole of zinc sulfate is equivalent to 1 mole or produces 1 mole of sulfate ions, then there will also be the same number of particles of sulfate ions. Now, in order to determine the I value of zinc sulfate, we simply add the number of particles divided by the original number of particles of zinc sulfate. So we have 40 plus 40 plus 60 divided by 100. And this will be equal to 1.4. Okay. Now take note that if the degree of dissociation is lower, then the I value or the dissociation factor is also lower. Hence, the extent by which a substance with a lower degree of dissociation is able to depress the freezing point of the solvent will also be much less. Now, how do we compare the tonic effect of different substances? In other words, how do we determine the amount of one substance having the same tonic effect in terms of freezing point depression as another substance? Remember that one quantity of any substance should, in theory, have a constant tonic effect if dissolved in 1000 grams of water. That is, 1 gram molecular weight of the substance divided by its I or dissociation value. Let us try to see how we can derive a formula that is based on that particular statement. Once again, you see here that 1.86 degrees Celsius times I is the freezing point depression of a gram molecular weight of any substance, whether electrolyte or non-electrolyte. And in order for us to determine the amount of that electrolyte or non-electrolyte that will have the same freezing point depression or tonicity as the body fluids, we should determine we should make use of the proportion with 0.52 degrees Celsius as the freezing point, the pressure of the body fluids. Now, let's suppose that we have two substances, substance A and substance B. We can rewrite the formulas like this. 1.86 degrees Celsius times the I of substance A equals its gram molecular weight or its molecular weight A divided by 0.52 degrees Celsius, which is the freezing point depression of body fluids, and molecular weight, we divide this by the weight of the substance A. Now let us transfer I over here. Now if you have another substance B, then the proportion will appear like this. Once again, we transfer the I value over here. Now, what you will see in this particular slide is that this is a constant value. This is also a constant value. And we can therefore say that this is equal to this. Rewriting the proportion, we have molecular weight of substance A divided by weight of substance A times the I value of substance A equals the molecular weight of substance B divided by the weight of substance A of B times the I of substance B. Now, if we want to determine the amount of substance A that is equivalent to, let's say, 1 gram of substance B, we can rewrite the formula in like this. So weight of substance A is therefore equal to the molecular weight of substance A divided by the I of A times the I of B over the molecular weight of substance B. Now, this is actually the derivation for the formula of the sodium chloride equivalent. If we assume that substance A is sodium chloride, then this will be the amount of sodium chloride, weight of sodium chloride equals the molecular weight of sodium chloride, which is 58.5 grams per mole, divided by its dissociation factor, which is 1.8, times the I value of any substance we want to compare sodium chloride to, divided by the molecular weight of that other substance. Now, this is actually the weight of sodium chloride that is equivalent, or that has an equivalent tonic effect as 1 gram of another substance. That's why we call this the sodium chloride equivalent or the tonicic equivalent. So according to this, quantities of two substances that are tonicic equivalents are proportional to the molecular weights of each multiplied by the I value of the other. And this is also the E value, or once again, the sodium chloride equivalent. Take note that the E value, or the sodium chloride equivalent, is the weight of sodium chloride that has the same tonic effect as 1 gram of another substance. Okay. Now, in order for you to easily remember this, just remember that the molecular weight of sodium chloride is grams of sodium chloride per mole of sodium chloride. And the molecular weight of any substance is the gram of that substance divided by their molecular number of moles of the other substance. Since the E value is defined as the weight of sodium chloride in grams, then the molecular weight of sodium chloride is supposed to be in the numerator per 1 gram of the substance. So the molecular weight of the other substance should be in the denominator. Let's try to solve some problems to illustrate the use of the E value. So the first problem is, what is the sodium chloride equivalent of boric acid, a weakly dissociated substance with a molecular weight of 61.8? Now remember that the E value is equal to the molecular weight of sodium chloride, which is 58.5, divided by its I value, which is 1.8, times the I value of boric acid, which is 1. Remember that boric acid is a non-electrolyte. Divided by the molecular weight of boric acid. So what we get is 58.5 times 1 divided by 1.8 divided by 61.8. And that will be equal to 0.526, or approximately equal to 0.53. And again, this is the gram of sodium chloride equivalent to 1 gram of boric acid in terms of tonic effect or freezing point depression. In the next problem, we calculate the sodium chloride equivalent for glycerine, a non-electrolyte with a molecular weight of 92. So we will just once again use the same formula. So 58.5 divided by 1.8 times 1. Remember that glycerine is a non-electrolyte, divided by its molecular weight, which is 92. The E value of glycerine is equal to 0.353, or approximately equal to gram of sodium chloride per gram of glycerol or glycerine. Now let's try to answer this problem. Procaine hydrochloride having a molecular weight of 273 is a 2-ion electrolyte dissociating 80% in a certain concentration. First, calculate its dissociation factor. Second, calculate its sodium chloride equivalent. And third, calculate the freezing point of a molar solution of procaine hydrochloride. So first, we determine the dissociation factor of procaine hydrochloride, which is considered as a 2-ion electrolyte dissociating 80% in a certain concentration. Now, its I is 80 particles plus 80 particles. So this is the cation, this is the anion, and then 20 particles, this is the undissociated procaine hydrochloride. And we divide this by 100. So the I value is equal to 1.8. Next, we calculate its sodium chloride equivalent. So the E value is equal to the molecular weight of sodium chloride, which is 58.5, divided by the I value of sodium chloride, which is 1.8. And then we multiply this by the I value of procaine hydrochloride, which is also 1.8, and divide this by the molecular weight of procaine hydrochloride, which is 273. Take note that the I values of sodium chloride and procaine hydrochloride are the same, so we simply cancel them out. So the I value is equal to 0.214. Next, we determine the freezing point of a molar solution of procaine hydrochloride. Once again, I will be presenting to you several solutions by which you can calculate this. First, we will make use of the proportion that we have mentioned before. Remember that a gram molecular weight of an electrolyte will have a freezing point depression that is equal to 1.86 times its I value. Okay, so the gram molecular weight of procaine hydrochloride is 273 grams. In 1,000 grams of solvent, its freezing point depression will be equal to 1.86 degrees Celsius times its I value, which is 1.8. Now, in order for us to determine the freezing point of the molar solution, we determine the freezing point depression of a molar solution of procaine hydrochloride. But the question is, how much of procaine hydrochloride are contained in that molar solution of procaine hydrochloride? Now remember that the definition of molality is that it is the weight of the substance divided by its molecular weight divided by kilogram of the solvent. Now, since we should be able to cancel out 1,000 grams here, then we will assume that the weight of the solvent that contains your procaine hydrochloride is the same, 1 kilogram or 1,000 grams. Now, we have a 1 molar solution. Then we just replace molecular weight with the molecular weight of your procaine hydrochloride, which is 273 grams per mole. So we multiply 1 molar by 1 kilogram by 273. So we get the weight that is also 273 grams. So what happens is that this side of the equation simply cancels out, and we are left with this formula delta TF equals 1.86 degrees Celsius times 1.8, and that will be equal to 1.86 times 1.8 is equal to 3.35 degrees Celsius. So the freezing point of a molar solution of procaine hydrochloride is equal to negative 3.35 degrees Celsius. Another way by which we can calculate this is through a formula, which is delta TF equals KF times M. However, take note that what we have is an electrolyte, so we introduce the I value in this formula. The delta TF, or the freezing point depression, is equal to the I value, which is 1.8, times the freezing point depression constant, or the cryoscopic constant of water, which is 1.86 degrees Celsius per molal solution of the solute, times 1 molal, which is the concentration of protein hydrochloride in the problem. So we simply cancel out the molal quantity, and we will now be able to solve for the delta TF, which is the same value, 3.35 degrees Celsius, or its freezing point is negative 3.35 degrees Celsius. Now let's try to solve this problem, which is very much similar to the previous problem. Sodium chloride is a two-ion electrolyte dissociating 90% in a certain concentration. Calculate its dissociation factor and calculate the freezing point of a molal solution. Now, take note that the I value is equal to, and the degree of dissociation of sodium chloride is 90%. So at the end of the dissolution, there will be 90 particles of sodium ion, 90 particles of chloride ion, and 10 particles of the undissociated sodium chloride divided by the original number of particles of the salt, and this will result in 1.9 I value. Next is we calculate the freezing point of a molal solution of sodium chloride. Let us just use the formula, that is delta TF equals I times KF times M. The I value of sodium chloride is 1.9. The KF of water is 1.86 degrees Celsius per molal solution. And the solution's concentration is 1 molal. So we have 1.9 times 1.86, and that will be equal to 3.53 degrees Celsius. Therefore, the freezing point of a molal solution of sodium chloride dissociating 90% in a certain concentration is equal to negative 3.53 degrees Celsius. Now, we can make use of our knowledge of the sodium chloride equivalent in order for us to determine the amount of sodium chloride that needs to be added to a solution to make it isotonic. Remember that any substance, whether electrolyte or non-electrolyte, will produce its own tonic effect. And the tonic effect can result in a freezing point depression or a change in the osmotic pressure of the solution. Another thing that you have to remember is that colligative properties are essentially additive. So if you have two or more substances in a particular solution, you just have to add the tonic effect of each of these substances to determine the total tonic effect in the solution. So for example, in this particular formulation, we have ephedrine sulfate and sodium chloride. Now, ephedrine sulfate contributes to the tonicity of the solution, and as well as sodium chloride, which is used as the tonicity adjusting agent. Now, the amount of ephedrine sulfate that is present in the formulation may not be sufficient to reach the same tonicity as the body fluids. So in order to increase or to reach the tonicity of body fluids, we have to add sodium chloride to the formulation. Okay, so let us look at this problem with the following formulation. Ephedrine sulfate with an E value or sodium chloride equivalent of 0.23 is 0.3 gram in the preparation. Then we are asked to add sodium chloride, a sufficient quantity of sodium chloride to make 30 milliliters of an isotonic solution using water. how many milligrams of sodium chloride should be used in compounding the prescription. Now, remember that in this particular problem, you have to follow certain steps in order for you to easily determine the amount of sodium chloride needed to make the solution isotonic. I normally start with determining the amount of sodium chloride that will make the solution isotonic. Assuming that only sodium chloride is present in the solution, I will determine the amount of sodium chloride that will make the solution isotonic. However, how do we know that? So, what is the number of grams of sodium chloride that would make the solution isotonic? Remember that previously I mentioned normal saline solution is essentially an isotonic solution of sodium chloride. Now, a normal saline solution contains 0.9% weight in volume of sodium chloride, or meaning we have zero point 0.9 gram of sodium chloride in 100 milliliters of the solution. Now, how do we determine this amount of sodium chloride that is isotonic in body fluids? So we also make use of the same formula that we have been using before, the proportion wherein 1.86 degrees Celsius times the I value of the substance will be the freezing point depression of a molal solution of an electrolyte dissociating 80% in the solution. And a molal solution of an electrolyte will actually contain the molecular weight, 58.5 grams, in 1,000 grams of water. Now, in order to make an isotonic solution, the freezing point depression of the solution should be 0.52 degrees Celsius. In order to determine the amount of the substance that is isotonic with body fluids, then we determine the value of X. Once again, we cancel 1,000 grams and we solve for the value of X. The value of X will be determined as 58.5 grams times 0.52 degrees Celsius divided by 1.86 degrees Celsius times the I value, which is 1.8. And this is equal to 9.09 gram of sodium chloride. Now, a solution of 9.09 gram of sodium chloride in 1,000 grams or 1,000 milliliters of water is considered to be isotonic, assuming that the volume of sodium chloride is negligible. Then we can say that the percentage weight in volume of sodium chloride that is considered isotonic is equal to 9.1 gram divided by 1,000 milliliters times 100, or that is equal to 0.9%. So always remember that an isotonic solution of sodium chloride is basically 0.9% weight in volume. So let's go back to the problem. First, solve the amount of sodium chloride to make the solution isotonic, and that is 0.9% or 0.9 gram per 100 ml. Now, since the solution, the volume of the solution is 30 milliliters, then we will multiply this by 30. This will be equal to 0.27 gram of sodium chloride. Now remember that this is only true if only sodium chloride were present in the solution. The next thing that you will do is determine the amount of ephedrine sulfate, or the next thing that you will do is determine the amount of sodium chloride that is represented by the amount of the ephedrine sulfate that is present in the solution. In the solution, we have 0.3 gram of ephedrine sulfate. And based on the problem, the E value of ephedrine sulfate is 0.23. So we multiply this value by the quantity of ephedrine sulfate present in the solution, because 0.23 is the number of grams of sodium chloride considered to have the same tonic effect as 1 gram of ephedrine sulfate. So multiplying these two values, what we get is 0.069 gram of sodium chloride represented by the quantity of ephedrine sulfate. Next, because in order to make the solution isotonic, we need to have 0.27 gram of sodium chloride, and the amount of um, sodium chloride represented by the ephedrine sulfate in the solution is 0.069. We need to gram. We need to subtract 0.069 from 0.27 gram of sodium chloride. And that will give us 0.201 gram of sodium chloride. So this is the amount of sodium chloride needed to be added to make the solution isotonic. And in milligrams, this is 201 milligrams of sodium chloride. So once again, let us review the steps that you need to follow in order to determine the amount of sodium chloride needed to be added to make the solution isotonic. First is you determine the amount of sodium chloride that will make the solution isotonic if only sodium chloride were present in the solution. Next, you determine the amount of sodium chloride represented by the quantity of the drug that is present in the formulation. And then you subtract the amount of sodium chloride represented by the quantity of the other drug in the solution from the amount of sodium chloride that will make the solution isotonic in order for you to determine the amount of sodium chloride to be added to make the solution isotonic. Now let us have another example. This time we have anhydrous dextrose, 2.5%, sodium chloride, a quantity that is sufficient to make 1,000 milliliters of an isotonic solution using sterile water for injection. The label should state isotonic dextrose and saline solution. How many grams of sodium chloride should be used in preparing the solution, given that the dextrose has a molecular weight of 180 grams per mole? Just like what we did before, the first thing that you will do is determine the amount of sodium chloride that will make the solution isotonic if only sodium chloride were present in the solution. And once again, we make use of the value that is 0.9% or zero point 0.9 gram per 100 milliliters of the solution. Then we multiply this by 1,000 milliliters, which is the volume of the solution that needed to be prepared. And the amount of sodium chloride that will make the solution isotonic becomes 9 grams. Next is we determine the amount of sodium chloride that is represented by the quantity of dextrose that is present in the solution. Now, the quantity of dextrose in the solution is not indicated in grams, so we have to compute for the number of grams of dextrose that is present in the solution. And that is equal to 2.5 grams per 100 milliliters times 1,000 milliliters. And this will be equal to 25 grams of dextrose. Now, given that we also don't have the E value for dextrose, we need to determine the E value of dextrose, or the quantity of sodium chloride that is represented by 1 gram of dextrose. So we use the formula that we used before, 58.5, which is the molecular weight of sodium chloride divided by the I value of sodium chloride times the I value of dextrose, which is 1, being a non-electrolyte, divided by the molecular weight of dextrose, which is 108. So the E value of dextrose is equal to 0.18. Remember that this is gram of sodium chloride represented by 1 gram of dextrose. Now, in order for us to, number three, determine the amount of sodium chloride represented by the quantity of dextrose in the solution, we simply multiply the E value, which is this one, by the quantity of dextrose that is present in the solution. So 25 grams times 0.18 gram of sodium chloride per gram of dextrose. So we get 4.51 gram of sodium chloride represented by the quantity of dextrose present in the solution. Remember that initially we have already determined that we need to have 9 grams of sodium chloride per 1,000 milliliters of the solution to make the solution isotonic. Now, we have also determined that 4.51 grams of sodium chloride are equivalent to the quantity of the dextrose that is present in the solution. So in order to make the solution isotonic, you only need to add 9 grams minus 4.51 grams of sodium chloride. And that is equal to 4.49 grams of sodium chloride. Now, what if we have a formulation that does not contain sodium chloride, but instead it contains another tonicity adjusting agent, which is boric acid? In this case, we have a formulation for zinc sulfate, which contains 0.06 gram of zinc sulfate, and we need to add a sufficient quantity of boric acid to make the solution isotonic. The volume of the solution is 30 milliliters. The solvent used is, of course, purified water. How many grams of boric acid with a molecular weight 61.8 should be used in compounding the prescription, given that the molecular weight of zinc sulfate heptahydrate is 288 and its I value is 1.4. In this case, I usually begin determining the E values of the substances that are stated in the formulation. Take note that in this particular problem, there are no E values indicated. So let us first determine the E value of each of these substances. So the E value of zinc sulfate is equal to the molecular weight of sodium chloride, which is 58.5, divided by 1.8, which is the I value of sodium chloride, times the I value of zinc sulfate divided by the molecular weight of zinc sulfate, that is 288. So the E value of zinc sulfate is equal to 0.158. Next, we determine the E value of boric acid from the molecular weight of sodium chloride, the I value of sodium chloride, the I value of boric acid, and the molecular weight of boric acid. And remember that we already calculated this before, and this is equal to 0.53. Next step, we determine the amount of sodium chloride that will make the solution isotonic. Remember again that normal saline solution is 0.9% or zero point 0.9 gram per 100 ml. And since we have 30 milliliters of the solution, then the amount of sodium chloride that will make the solution isotonic is 0.27 gram if only sodium chloride were present in the solution. Next, we determine the contribution of the quantity of zinc sulfate to the tonicity of the solution by making use of the E value of zinc sulfate. So the E value of zinc sulfate is 0.158, and the quantity of zinc sulfate in the solution is 0.06 gram. So this will determine the amount of sodium chloride that is represented by the quantity of zinc sulfate in the solution. So this will be equal to 9.48 times 10 to the negative 3 gram. Or this is equivalent to 0.00948 gram, or simply 9.48 milligrams. Next is we subtract this value from this value to determine the amount of sodium chloride to be added to make the solution isotonic. And that will be equal to 0.27 gram minus 0.00948 gram, and that is equal to 0.261 gram of sodium chloride. However, in the formulation, we will not be using sodium chloride as a tonicity adjusting agent, but instead we will be using boric acid. Take note that boric acid has an E value of 0.53, and this essentially means 0.53 grams of sodium chloride are represented by 1 gram of boric acid. So in order to determine number 5, the amount of boric acid to make the solution isotonic, we simply divide 0.261 gram of sodium chloride by the E value of boric acid, which is 0.53. And again, that's gram sodium chloride per gram of boric acid. So we cancel gram of sodium chloride and we get the gram of boric acid. And that will be equal to 0.49 gram of boric acid. So that's it. That's how we solve for the amount of boric acid necessary to make the solution isotonic. Now let us try to solve another problem. In this particular problem, you can see that neither sodium chloride or boric acid is present in the formulation, but instead, potassium nitrate is used as a tonicity adjusting agent. There are some occasions when we need to consider the compatibility of the drugs that are present in the formulation in order to choose for the appropriate tonicity adjusting agent. In the case of silver nitrate, remember that presence of chloride will result in the precipitation of silver chloride, which is a white earthy precipitate. Um, so sodium chloride in this case is not possible as a tonicity adjusting agent. Another reason, no, why we don't see boric acid is that because of the basicity of boric acid in the solution. Although boric acid is considered to be an acid, it is a very weak acid that in solution it is slightly alkaline. Now, the presence of boric acid in solution will actually produce hydroxide ions, which can result in the precipitation of silver oxide from the solution. So it is also not possible for us to use boric acid. So the best tonicity adjusting agent for silver nitrate is potassium nitrate. Now, just a little background on the use of silver nitrate as an ophthalmic drop. This is used for neonatal gonorrhea as a prophylaxis. Now, in this particular problem, we are asked to determine how many grams of potassium nitrate with a molecular weight of 101, a 2-ion electrolyte with 80% dissociation, should be used in preparing the solution. Silver nitrate is a 2-ion electrolyte with 80% dissociation. So just like what we did before, the first thing that we will do is we will determine the E value of these substances. So we determine the E value of silver nitrate and the E value of potassium nitrate. So the E value of silver nitrate is 58.5 divided by the I value of sodium chloride, which is 1.8. Then we multiply this by The I value of silver nitrate, which is also 1.8 because it is a 2-ion electrolyte with 80% dissociation, divided by its molecular weight, which is equal to 170. We cancel 1.8, so we are left with 58.5 divided by 170. And this will be equal to 0.344. Next, let us determine the E value of potassium nitrate. So we again make use of the molecular weight of sodium chloride, which is 58.5. We divide this by the I value of sodium chloride, which is 1.8, and we multiply this by the I value of potassium nitrate, which is also 1.8, being a 2-ion electrolyte with 80% dissociation, and its molecular weight that is 101. Next, we cancel out 1.8. We are left with 58.5 divided by 101, and this gives us an E value that is equal to 0.579. Remember that again, once again, these values essentially mean these are the grams of sodium chloride represented by gram of the substance, silver nitrate and potassium nitrate, respectively. Next, we determine the amount of sodium chloride that will make the solution isotonic if we will be using sodium chloride as a tonicity adjusting agent. And the amount of sodium chloride that will make the solution isotonic is equal to zero point 0.9 gram per 100 ml times 15 milliliters. So this will be equal to 0.135 gram of sodium chloride. Next, we determine the amount of sodium chloride represented by the amount of silver nitrate that is present in the solution. Now, the exact quantity of silver nitrate is not necessarily written in grams, so we need to still determine the number of grams of silver nitrate present in the solution by making use of the percent strength. So 0.5% is equal to 0.5 gram per 100 milliliters of the solution. And then we multiply this by 15 milliliters. We get 0.075 gram of silver nitrate present in the solution. Then, using the E value of silver nitrate, we will be able to determine the sodium chloride equivalent to that quantity of silver nitrate. So 0.075 gram of silver nitrate times 0.344 gram of sodium chloride per gram of silver nitrate will be equal to 0.0258 gram of silver chloride. Since we need to have 0.135 gram of sodium chloride to make the solution isotonic, we will subtract 0.0258 gram of sodium chloride represented by the quantity of silver nitrate in the solution to determine the quantity of sodium chloride that will make the solution isotonic. And that is equal to 0.1092 gram of sodium chloride needed to be added to the solution to make the solution isotonic. Because we will not be using sodium chloride as our tonicity adjusting agent, we will make use of the E value of potassium nitrate to determine the amount of potassium nitrate that will make the solution isotonic. And that will be through 0.1092 gram divided by 0.579, and this will be equal to 0.189 gram of potassium nitrate, or approximately equal to 0.19 gram of potassium nitrate. That is how we make use of the sodium chloride equivalents in order for us to determine the amount of sodium chloride that will make a solution isotonic in pharmaceutical preparations. Aside from the sodium chloride equivalent, we can also make use of the freezing point data in determining the tonicity of the solutions. Freezing point data or the freezing point depression data can be used in isotonicity calculations when the agent has a tonic effect and does not penetrate the biologic membranes in question, for example, the red blood cells. Remember, once again, that a pharmaceutical that has a freezing point of negative 0.52 degrees Celsius is considered as isotonic. You will see in your textbook that there is a list of pharmaceutical agents with their freezing point depression. Take note that the freezing point depression values that are listed in this particular table are the freezing point depression values of 1% solutions of these pharmaceutical agents. Now, in order for us to determine the amount of the tonicity adjusting agent that needs to be added to the solution to make the solution isotonic, we first consider the freezing point depression due to the presence of the other substance that is present in the solution. In order for you to understand what that means, let us try to solve some problems. So in this particular problem, we are given two substances present in the solution. We have procaine hydrochloride with a freezing point depression of 0.12 if the solution is 1%, and sodium chloride with a freezing point depression of 0.58 degrees Celsius if the solution is 1%. We are asked to determine the amount of sodium chloride in grams that will be used to make the prescription, which has a volume of 100 milliliters isotonic. Now, take note that in this method, we begin with our knowledge that an isotonic solution has a freezing point depression of 0.52 degrees Celsius. Now, procaine hydrochloride in the solution is already 1%, and it contributes to as much as 0.12 degrees Celsius um, in the freezing point depression of the solution. Therefore, in order to determine the amount of sodium chloride that needs to be added to make the solution isotonic, we simply subtract the freezing point depression of 1% procaine hydrochloride from 0.52 degrees Celsius, which is the freezing point depression of an isotonic solution. So this is equal to 0.40 degrees Celsius. So this is the remaining freezing point depression that needs to be provided by the amount of sodium chloride that you will add in the solution. The next step that we will use is that we will simply make use of proportion to determine the concentration of sodium chloride that will make the solution isotonic, knowing that 1% sodium chloride gives a freezing point depression of 0.58 degrees Celsius. Now remember that the concentration plus the degree of dissociation of the substance essentially is directly related to the freezing point depression of the solution. 1% solution of sodium chloride is known to have a freezing point depression of 0.58 degrees Celsius. So in order for us to achieve a freezing point depression of 0.40 degrees Celsius, the amount of sodium chloride that we need to add to the solution can be computed by a simple ratio and proportion. So we solve for the value of x. So the value of x is equal to 1% times 0.40 degrees Celsius divided by 0.58 degrees Celsius. So that value is equal to 0.4 divided by 0.58, and that is equal to 0.69%. This is the percentage of sodium chloride that must be present in the solution. The third step that we will do is we simply multiply the volume, which is 100 ml, by this concentration, which is 0.69% or zero point 0.69 gram per 100 ml. So we now have this answer: 0.69 gram of sodium chloride needs to be added to make the solution isotonic. Now let us solve another problem. This time, we are given a soluble homatropine hydrobromide with a freezing point depression of 1% solution, equivalent to 0.11, and the solution's volume is 15 milliliters. We are asked to determine the number of grams of boric acid that should be used in compounding the prescription. Now, the E value of boric acid is stated here. Although we know already from calculation that it's supposed to be 0.53, in this case, the E value is stated as 0.52, so we will make use of that value. Just like what we did before, step number 1 is subtract the freezing point depression contributed by the drug that is present in the solution from the freezing point depression of an isotonic solution, which is 0.52 degrees Celsius. And take note that the concentration of soluble homatropine hydrobromide in the solution is also 1%. So we simply subtract 0.11 degrees Celsius from 0.52 degrees Celsius. So we have 0.41 degrees Celsius. And this freezing point depression needs to be provided by the tonicity adjusting agent, which is your boric acid. Now, the freezing point depression of 1% solution of boric acid is not stated in the problem. So we will make use of sodium chloride equivalent in this case. So what we can use is the freezing point depression of sodium chloride, which we knew from the previous problem. So we knew that 1% solution of sodium chloride has a freezing point depression of 0.58 degrees Celsius. In order for us to attain a freezing point depression of 0.41 degrees Celsius, X is the percentage of sodium chloride that must be present in the solution. So X is equal to 0.41 degrees Celsius times 1% divided by 0.58 degrees Celsius. So X here now becomes equal to 0.71%. The third step is we determine the amount of sodium chloride that is equivalent to this concentration if the volume is 15 milliliters. So we multiply 15 milliliters by 0.71 gram divided by 100 milliliters. So we have 0.1060 gram of sodium chloride. Now, we are not yet done because sodium chloride is not used as a tonicity adjusting agent in this particular formulation. So we will make use of the E value of boric acid to determine the amount of boric acid that will make the solution isotonic. So 0.160 gram of sodium chloride divided by the E value of boric acid, which is 0.52 gram per gram of sodium chloride per gram of boric acid. So this will be equal to 0.2 gram of boric acid. In the last problem, not only do we have one additional drug substance in the formulation aside from the tonicity adjusting agent, but we have two. And we are given the E value of phenylephrine hydrochloride as well as the freezing point depression data of chlorobutanol and sodium chloride. We are asked to determine how many milliliters of 0.9% solution of sodium chloride shall be used in compounding the prescription. So in this particular problem, the first thing that we will do is make use of the freezing point depression to determine the to determine the amount of the other substances that needs to be present in the solution to make the solution isotonic. Now, we can see that chlorobutanol is only present in the solution as in a concentration that is 0.5%. Now, we are given the freezing point depression data of a 1% solution of chlorobutanol, and that is equivalent to 0.14. Remember that the freezing point depression is essentially directly proportional to the quantity of the solute that is present in the solution. So if we only have 0.5% of chlorobutanol in the solution, we can solve for the freezing point depression of that substance using the freezing point depression of 1% solution of chlorobutanol, which is 0.14. So this will be equal to 0.07 degrees Celsius. Now that we know that 0.5% chlorobutanol contributes to only 0.07 degrees Celsius in the freezing point depression of the solution, we can subtract this value from 0.52 degrees Celsius, which is the freezing point depression of an isotonic solution. And this is equal to 0.45 degrees Celsius. Now, this is the freezing point depression that needs to be provided by both sodium chloride and your other substance, which is phenylephrine hydrochloride. Because both are present in your formulation. So what we can do is we can make use of the freezing point depression data of sodium chloride to determine the amount of sodium chloride that will give 0.45 degrees Celsius of freezing point depression. So remember that 1% sodium chloride has a freezing point depression that is 0.58 degrees Celsius. And because 0.45 degrees Celsius is the required freezing point depression that remains to be provided by the other two substances, we can solve for the amount of sodium chloride that will give that freezing point depression X. So this will be equal to 0.45 divided by 0.58. And that is equal to 0.78% or 0.7759 percent of sodium chloride that will make the solution isotonic. Now, take note that we can actually determine the amount of sodium chloride that is represented by phenylephrine hydrochloride using the E value of phenylephrine hydrochloride. But before that, we must determine the grams of sodium chloride that is represented by 0.78% in the 15 ml solution. So 15 milliliters of the solution times 0.78 gram per 100 ml is equal to 0.12 gram of sodium chloride. Next, step number 4. We determine the amount of phenylephrine hydrochloride present in the 15 ml solution, and that is 1% or 1 gram per 100 ml. And this will be equal to 0.15 gram of phenylephrine hydrochloride. Now we make use of the E value of phenylephrine hydrochloride that is stated in the problem to determine the number of grams of sodium chloride represented by the quantity of phenylephrine hydrochloride. So once again, we simply multiply the E value of phenylephrine hydrochloride by 0.15 gram to determine the number of grams of sodium chloride represented by that quantity of phenylephrine hydrochloride. And that amount is 0.48 gram sodium chloride. Now, step number 5 is we knew from our previous calculation that we would need 0.12 gram of sodium chloride to make the solution isotonic together with 0.5% chlorobutanol. However, aside from sodium chloride, there is also phenylephrine hydrochloride that is present in the solution. And the quantity of phenylephrine hydrochloride present in the solution has the same tonic effect as 0.048 gram of sodium chloride. So all we need to do is we subtract 0.048 from 0.12 gram. To determine the amount of sodium chloride that needs to be added to the solution to make it isotonic, together with chlorobutanol and phenylephrine hydrochloride. And that will be equal to 0.072 gram of sodium chloride. Now we are not yet done because we are asked to determine how many milliliters of 0.9% solution of sodium chloride needs to be used in compounding the preparation. So that will be our step number 6. So what we will do is we will simply divide 0.072 gram by 0.9 gram per 100 milliliters to determine the number of milliliters of 0.9% sodium chloride. And we get a value that is equal to 8 milliliters of 0.9% sodium chloride. So that's how you combine both. You combine the two methods of calculating the tonicity of the solutions, the sodium chloride equivalent, and the freezing point depression data. That ends our discussion on isotonic solutions. I hope that you learned something from this discussion. Thank you.